In this video, I will try to explain the historical development of electrostatics and the mathematical descriptions of all the laws of electrostatics.
So first let's talk about the forces between two charges, which is now known as Coulomb's law. So for instance, if you have two charges Q1 and Q2 which are separated by distance r12, and if you want to calculate force on Q1 due to Q2 which is F12, or if you want to calculate the force on 2 due to 1 which is F21, the force F12 is equal to 1 upon 4 pi epsilon 0, the strength of the charge Q1 and the strength of charge Q2 divided by the distance r square. This is in the direction r12. If the force was F21, then the direction will be r21. The first experimental proof of this r square dependence was actually done by Cavendish in 1772. Actually, it was quite difficult to design or imagine such a system which can really prove the r square dependence. Actually, what he did, he took a hollow sphere which had a solid sphere in it, and he connected by a wire, and then he distributed the charge on the hollow sphere by external source. Then he calculated the force. So now we have seen the force between two charges. The immediate question one would like to ask: what happens when you have collection of charges? For instance, if you have a charge Q which is surrounded by four charges Q1, Q2, Q3 and Q4, which are separated by the distance r1, r2, r3 and r4, then the force on Q is simply the addition of the force due to Q1 on Q in the direction r1 and the force due to Q2 on Q in the direction r2 and the force due to Q3 on Q in the direction r3 and the force due to Q4 on Q in the direction r4. We can also write this in a very short way by using the summation notation, and we can also replace our unit vector by the r vector by putting here r cube. So the force on charge Q due to all of the different charges, it doesn't matter how many we have, it's just simply a vector addition of the forces due to all the charges around it. So now let's see what happens when you have a uniform charge density. So if you have a uniform charge density, we would like to calculate a force due to the uniform charge density at a particular distance. For example, if you have a rod which has a length L and it has charge density per unit length lambda, then if we have a charge Q at a distance x, we want to calculate the force on charge Q due to this rod which has a uniform charge density. So what we would like to do is to calculate the force on this charge Q due to this length dy. So this dy has some charge and we want to calculate the force on this Q. So the force F is equal to 1 upon 4 pi epsilon 0 Q, the strength of this charge, and the charge density of this length. So we have dy here from here to here which has some charge. We multiply with the charge density and we get the total charge, and then we divide it by the square of the distance, and the distance is x square plus y square. So the square of this is x square plus y square in the direction x hat minus y hat. Then we also have to make it a unit vector by dividing it with the magnitude of the distance between dy and q. So the force is in this direction, so you have the negative sign here. The force in y direction is going to be 0, so we will calculate the force only in x direction. And the force in x direction is q times lambda from here, and then we have x here and times dy divided by this whole factor, x square plus y square to the power 3 by 2. Then when we do the integration, we get q times lambda divided by 4 pi epsilon 0 into L divided by L square plus 4x square and root of it. Then we can take a limit L tending to infinity. So what it means is, if you have rod which is infinitely long, then what will be the force on charge Q at a distance x? So in this case, we really have to take the limit because you put L equal to infinity and this becomes infinity divided by infinity form. So we take the limit by taking the derivative on the numerator and the denominator, and then we get 1 over x dependence of the force. So now we have seen a couple of examples on how to calculate the force between charges, the distribution of charges, or the uniform charge density. Then let's talk about the electric field. So the electric field is basically the force per unit charge. So if you have a unit charge, then we would like to see what is the force on this charge due to a charge density. For example, if you have a volume which has a charge density per unit volume rho, then we would like to calculate the force on this charge due to this volume which has a distribution of charge. So the distance from origin to the Q is R, and the distance between origin and the center of the volume is R prime. Then the distance between the charge density and the charge is R minus R prime. So the force between this charge density and the test charge Q is 1 upon 4 pi epsilon 0 integration dV times rho, which is basically the charge in the volume dV. So we are multiplying dV with the charge density rho, so we get the total charge in the volume dV. Then we multiply by the distance vector and divide it by the magnitude of the cube of the vector. So to calculate the electric field, we have to integrate this. So when we integrate the charge density rho over the volume, we get Q prime, which is the total charge in this volume, and this vector as it is. So this is the electric field. So now if we want to visualize how the electric field looks like due to a point charge, and the electric field due to a point charge looks like this. So if you have a charge here, then the electric field will go radially outward like this.
So after establishing what is an electric field due to a point charge, we would like to see a couple of other examples in which we can calculate the electric field. For example, let's take the case of a dipole. For example, if you have two charges, negative and positive charge, which are separated by distance 2a, the electric field due to these charges or this dipole on a test charge which is kept at a distance r, then simply the electric field, which is force per unit charge, is equal to 1 upon 4 pi epsilon 0 q, the strength of the charge, into the distance divided by the magnitude of the distance vector, minus the electric field due to the negative charge, that's why we have a minus here, times r plus az, the distance from this charge, divided by the cube of the magnitude of the distance vector. Now we have to do a little bit of simplification just by expanding these terms, and then we use the condition that a is very small. A is so small that a is almost tending to 0. That's why these positive and negative charge are so close, and the q is very large compared to the distance, and we also assume that 2qa is equal to p. Then the electric field at distance r is 1 upon 4 pi epsilon 0 3 times p dot r in r hat direction minus p divided by r cube. So with this method of calculating force per unit charge, we can calculate the electric field for many situations, but in many other situations it becomes very complicated to really calculate the electric field. So that's when the Gauss's law comes in, which says the flux of an electric field out of any arbitrary closed surface is proportional to the charge enclosed in it. So if you have any charge which is enclosed in a volume, then the electric field outside of this enclosed surface is directly proportional to whatever the charge which is enclosed in the surface. For example, if you have a volume, a spherical volume with the radius r, which has the charge density per unit volume rho, then E dot ds is equal to Q enclosed, the charge enclosed, divided by epsilon 0. On the left side we can integrate all over the surface, and on the right side we can calculate the total charge which is enclosed in this volume. So the surface area of a sphere is 4 pi r square, so the left side becomes electric field times 4 pi r square, which is equal to 1 upon epsilon naught, and the volume of the sphere in which we have the charge density, which is 4 by 3 pi r cube times the charge density. So now after simplifying this equation, we can see pretty easy that electric field is nothing but 1 over 3 rho times r vector divided by epsilon naught. With the Gauss's law, we can calculate the electric field at any point in space if the charge distribution is known. But in reality, it sometimes becomes very difficult to understand or to know what is the exact charge distribution. In that situation, we would like to use the Helmholtz theorem for electric field. So what this theorem says is, it is always possible to determine the electric field everywhere else at any other point if we know electric field at a particular point due to a charge distribution. We don't really need to know what the charge distribution is. If we know at a particular point due to that charge distribution what is an electric field, then we can calculate at all other points. For example, if you have a charge q in a sphere, then the electric field at the distance capital R due to this charge is 1 over 4 pi epsilon naught q, the total charge, divided by r square. And the electric field at a small distance r is 1 upon 4 pi epsilon naught q divided by r square. Then we multiply these by r square and divide it by r square as well. Now this value 1 upon 4 pi epsilon naught q times r square is nothing but the electric field at the distance capital R. So the electric field at distance small r is the electric field at distance capital R multiplied by the capital R square divided by small r square. So we can know the electric field at a distance small r is related to the electric field at the distance capital R, which is 1 over r square dependence. Now we would like to ask, does it work everywhere? Well, no, because this only works when we have an electric field which is completely uniform. If we have electric field which is non-uniform, then it is impossible to know the electric field everywhere else. For that, we need more information than just the electric field at a particular point. So if we have a non-uniform electric field, then what else we need to know to determine the field everywhere in the space? For example, if we have a wall which has a non-uniform electric field distribution, and if we want to know what is the electric field at all the other points in the space, then we must know the perpendicular component of the field at each point and the divergence of the field and also the curl of the field. If we know these three things, then we can determine the electric field everywhere else. This is the Helmholtz theorem for electric field. In the next lecture, I will try to explain what is a divergence for an electric field, how to calculate the divergence of an electric field, what is a curl of an electric field, and how to calculate the curl of the electric field. And based on these three things, how do we calculate the electric field everywhere else in the space.